I'd like to start this presentation just by highlighting that most of what I'm presenting, the AFM work that I'm presenting, was performed by a PhD student Fengyuan Zhang, who is graduating soon, I hope. Sorry, let me find my spotlight. Okay, thank you. Good. Okay, so the next slide shows an overview for my talk. It seems to be slightly delayed. Okay, so a lot of you in this session will be familiar with PFM. PFM, of course, is a contact mode technique where we have a conducting cantilever and we apply a bias and we use it to measure the piezoelectric activity of a sample. In ferroelectric materials, this allows us to map out domains and understand ferroelectric switching. And what I'd like to talk to you about today is the range of forces that we can apply using AFM and how we can use it to study ferroelectric materials. So depending on your sample, typical ferroelectric samples will tend to use a relatively stiff cantilever, maybe a couple of newtons per meter or higher. And this is to minimize the electrostatic contributions to the signal that we measure. But if we apply a little bit higher force, what we find is that in certain materials, such as mixed phase bismuth ferrite, we can cause a structural phase transition from, say, a mixed phase or a bias-induced T phase to a mechanically induced mixed RT phase, where T is tetragonal and R is rhombohedral. So we can change the topography, as you see here, where you have the raised features are mostly T phase, and then we can go to this mixed phase structure. And it doesn't cause switching of the material, but it does cause a change in the PFM amplitude. And what we've been working on more recently is what happens when we apply a bias to our bismuth ferrite sample to our BiFeO, and well, we apply a force pressure with our tip. So as we apply higher and higher forces, we see that we can change the switching behavior of the material. And if we measure the current as well, we can start to get a switching induced current, as shown here. So we push into the material, and as we're switching, we can see that we'll develop a peak, a current peak. And this current peak will shift, just like the course of field is changing here, the course of bias is changing here. You can see it shift to lower and lower voltages as we increase our force, and we also increase our currents. Now, if we apply even larger forces, we're able to machine the material. We can carve out a nice harp from the UCD logo or make nanostructures. And this is what I'm going to be talking about in the rest of this lecture. Here shows a quick little animation. I'm not sure if the refresh rate will work well for Zoom, but you can see as the tip is moving across the sample, we can actually carve out structures, carve out nanostructures and test their ferroelectric properties and test the influence of the mechanical force applied on the ferroelectric behavior. So this is what I'm going to be focusing on in my talk. So now, why is current interesting to measure? So if we think of a ferroelectric memory where you can switch the polarization between up and down, between a 0 and 1, storing bits of information, one of the ways to measure, to read out this information is through the switching current. So here you can see two displacement current peaks, both for negative switching and positive switching up and down. And so we can use this to read out the material, to read out the polarization state. Now, as we go to smaller and smaller memory elements, this becomes important for high density data storage. Here you can see switching current for these roughly 300 nanometer ferroelectric capacitors, and you can see the polarization current, the polarization versus voltage here. So this is 10 picoamps for about a 300 nanometer size. But as we go to higher density and smaller elements, smaller sized features, we're going to have smaller sizes and lower currents. So having a mechanism to enhance the current might be useful, beneficial for reading out the polarization state in ferroelectric memories. Here's an example of 200 nanometer capacitors, gold capacitors on a doped BiFeO film. And the researchers found that the injected current could be orders of magnitude higher than the switching current, than the normal switching current. And they explained this by considering that during switching, the barrier height can change, allowing charge to cross the dead layer that's present at the surface of ferroelectrics. This injected current can be much higher than the displacement current, and so maybe this could be a mechanism for enhancing the current. Similarly, if we look at this dead layer on the surface of ferroelectrics, and BiFeO also has this dead layer can act as a series resistance that would suppress the current, especially at small scales when you consider the tip as the top electrode. If we look at an equation for tunneling across an interface or tunneling across a dead layer, you can see that it depends on the barrier height. It depends also on the thickness of the interface layer. So we consider that maybe if we can control the thickness of this dead layer, perhaps through applying a mechanical force, a mechanical pressure to squeeze it, to pinch it, that maybe we can influence the currents. So by applying a large force with a tip, can we modify this dead layer? Will it also change the barrier height? Will it squeeze the dead layer and allow more current to tunnel and increase our injected current over our normal switching current? So this is the BiFeO sample that we looked at. You can see here that it has a normal kind of topography and behavior for mixed phase bismuth ferrite that we're studying. It switches perfectly fine. These are hysteresis loops recorded with the AFM tip. We can apply a DC bias during scanning and cause the material to switch into up and down domains. So we're happy enough. It's a good quality film. And so as I mentioned before, what we can do is start studying, and these measurements were performed across a grid, across the sample. We can start studying what happens to the hysteresis, the switching, as a function of applied force. So going from 50 nanonewtons up to 925 nanonewtons in this case. And you can see a pinching of the thickness. So the coercive field is changing. The effective coercive field is changing. The switching voltage is changing in both directions. So it becomes easier to switch in both positive and negative sides. And we can map this here. So you can see that the coercive voltage is becoming lower on the positive side, but also lower on the negative side. And this is kind of an interesting way of thinking of being able to tune the coercive field, have a lower switching voltage just by application of a force. Okay, so we also used conducting AFM. So again, a contact mode technique using a conducting cantilever, and you're applying a bias and measuring the current that flows. And we did that essentially while switching the material. So you can see that we have a current peak at the switching event, and that's shown more clearly here where I overlay hysteresis loop showing the switching. And the images on the data on this slide is recorded at 750 nanonewtons. So to confirm to ourselves that this was related to the switching event, here you can see that we do a setting pulse. So we're switching it in one direction, and then we're doing a train of pulses in the opposite direction. So only on the first event should we have switching, and if the current is related to the switching event, then we would only have the current when we're applying the bias that switches it. So as you can see here, only on that first cycle do we have switching. Similarly, in the other direction, when we're applying negative bias, also setting pulse in one direction and then switching, only on that first switching event do we have current. So we attribute this current to a switching related current. Okay, so I kind of gave away everything I was going to present at the very beginning of my presentation. And here again, I'm showing what's happening to the current as a function of force. So we don't quite see the switching. Maybe we don't have a strong enough contact, or the currents are too low. But as we start increasing the current, the force higher and higher, we start to see the current peak. You see the current peak here associated with switching. As I said, this current peak is going to lower and lower voltages because it's becoming easier to switch under the applied force, and the currents are getting higher. So you can start to think that this gives us a mechanism, a way of tuning the tunneling or the injected current or the switching related current to be able to have kind of orders of magnitude higher. We wanted to check what happened when we started decreasing the force. So here we're going from 50 to 750. Here we're going back down to 50 nanonewtons. And again, you can see a similar trend is following. And if we look at the charge associated with this current for the time it takes to record this data, we can estimate the polarization. And this polarization that we're estimating is orders of magnitude higher than the normal polarization of bismuth ferrite. And so we think that there's some other mechanism that's related to this current that we're measuring. Similarly, you can see this V shape in the voltage peak location as a function of force, showing that you have a certain ability to effectively tune the switching voltage by mechanical force. Okay, so what we think is happening based on the discussion that I had at the beginning, the first few slides, is that as we're pushing down, we're squeezing that interface layer, we're squeezing that dead layer a little bit. And so that might enhance the tunneling and it might enhance the thermionic current. So this, in this part of the work, we identified the polarization switching injected currents. We increased the loading, by increasing the loading force, we enhanced the current for both positive and negative biases. And by increasing the loading force, we decreased the switching voltage for both positive and negative biases. And we think that this behavior might be related to this schematic shown here, that the barrier height is slightly reduced, and that the thickness of the dead layer, the interfacial layer, is reduced. So the question for us became, well, is there a limit to how much current we can get? What happens if we push even harder, apply more force? Do we get more current, or do we start to damage the film? And then if we can damage the film, can we create structures, and can we inject functional states? Can we write functional states in those structures? And if we can make those structures, do they still switch? Are they still ferroelectric, or do we damage them? So humans have been fascinated for quite some time in terms of carving things and making structures. So this, from the prehistoric level to ancient Egypt and an early depiction of a lathe, to more modern lathe and cutting tools that often employ a diamond cutting tool. And even AFM is used to look at the surfaces that are carved by these diamond cutting tools. And now single crystal diamond tips are commercially available. And so this work was partially motivated by, well, why don't we just do this with an AFM tip as well? We can precisely carve structures. We can also use the same tool for imaging the structures. Okay, so this technique is fairly well established, and it comes under a number of different names, from nanosculpting to what we tend to call machining or nanomechanical machining. And the idea is quite simple, I think, to understand for everyone, that you're basically pushing the tip into the material. So you have to think about the material properties and about the tip properties and the cantilever properties. And then you're either indenting to make a feature, or you're pushing down and drawing a line, drawing a scratch to make a feature. What's interesting for me about this technique is that it can be used for imaging, but also tomography. You can measure properties as you're removing material. And you can also, as part of this technique, you can gain insight into materials properties, and also that you can simultaneously detect the process. So you can see that you're actually removing material, which I think is nice. And this has been applied to a variety of different materials. Here are silicon nanochannels. Here's a photograph that's been transferred into aluminum. Here's a polycarbonate nanoarray. And here's an example of 3D tomography, so of a conductive filament. So you can kind of remove material a bit at a time and look at the conduction as you go down. Now, in terms of ferroelectric materials, I also mentioned at the beginning the idea of going to smaller and smaller feature sizes and nanostructures for higher density materials. That's one target, one application. And there are a variety of different top-down and bottom-up approaches for this, including focused ion beam milling, mask-assisted pulse laser deposition, so depositing through a mask or some kind of self-assembly. And so we're curious to see where an AFM-based machining approach fits into this. There might be limitations in the nanostructure size due to ion injection damage, and certainly there might be a mask limitation at some point here. So in terms of tip-assisted approaches in ferroelectric materials, using a local AFM tip that can be heated up has been used for crystallizing ferroelectric structures. AFM tip has been used to carve out holes, and then those holes are kind of filled in with a ferroelectric polymer. And Brian Huey's group at UConn has recently published a couple of really nice papers using this technique for tomography of ferroelectric domain structure. So this is really cool work that they're doing. So what we proposed doing was using that same film that we've been talking about before. It has an overall nice structure, and it has this mixed phase structure. It's about 50 nanometers thick, and we were using a tip that's 100 newtons per meter. And this work goes back to at least 2017, and I think this was the first data that Feng Yuan got, where she was able to just make a scratch, make a box, and from there we started exploring it in greater detail. So first we wanted to understand how we could machine different regions. So we can play around with drawing lines that have certain separations, so 10 nanometers up to 60 nanometers, and applying different loading forces and kind of doing an array. So within this whole image, we have a lot of data that we can analyze. We can look at the roughness on the inside, we can look at how much material is removed, and so on. So what we wanted to do is understand the parameter space for this particular material so that we could say, okay, if we want to have a particular roughness surface, or we want to have a particular amount of material removed, we can kind of have a lookup table and be able to see what we need to be able to make the structure or surface that we want. So here you can see what we would see in terms of depth as a function of force, roughness as a function of force, and we could more or less fit it to an established model for predicting the depth of a nanochannel using a machining approach. You can see it works a little bit better at higher forces and not so well at the lower forces, but this might be due to the model not accounting for factors like the structural phased transition that we have in our material, removal of machined pile-up material, elastic recovery, and friction. So we could also, at a particular separation, vary the velocity and see the influence of the tip velocity on the depth, on the removal of material, but also on the polishing or smoothness of the material. So we found that a smaller separation between adjacent lines resulted in a larger depth, as you might expect, and the depth is relatively unaffected by different velocities in the range that we studied, and the roughness increases with increasing force and depth. And this highlights that there are certainly different regimes in tomographic measurements of ferroelectric materials, where you can have a material removal, a plowing regime, and you can also have a polishing regime where you're removing just a limited amount of material at a time. And that's probably most suitable for the tomographic approach for imaging ferroelectric domain walls as a function of depth. Since the tips that we're using are conducting, they're doped to be conducting, we can also look at the film thickness. So we can remove material and then to see it at which point we have conduction to the bottom electrode. So it's kind of like a built-in monitoring of the process. Okay, so we wanted to figure out what's the thinnest line we can scratch to be able to understand then what's the smallest nanostructure we could machine. So we looked at the material and we loaded the cantilever, loaded the sample at different orientations and drew a circle. And you can see for these different orientations, there's always a region where you have the thinnest line. And this kind of makes sense when you start to think about a cantilever twisting. So perhaps if we had used a stiffer cantilever, a cantilever with a stiffer torsional stiffness, higher torsional stiffness, we wouldn't have seen that effect so dramatically. But it tells us that we really have to be pushing in the direction of the cantilever. Then we looked at what's the minimum width we could draw. So it looks like around 17 micronewtons is where we're starting to get these lines. You can see that the depth is getting higher with increasing force and with increasing velocity. And I'm only showing depth versus force here, but you can plot depth versus force, width versus force. You can also determine what the cone angle, so what's that aspect ratio of the trench you've drawn. Okay, so using kind of optimized parameters, we were able to make a hashtag here. And so the smallest feature size that we saw was about 90 nanometers, and it still switched, and we could do PFM switching of it and imaging. Okay, so we were happy that the ferroelectric properties of the fabricated nano island were retained. We did make a variety of different types of structures. We were interested to see maybe if there were some size effects. So as we go to smaller and smaller island sizes, do we start to see a pronounced effect on the switching? We tried making various types of arrays and also some other nanostructures. So this one's a little bit larger, but still switches. And eventually we figured out kind of the optimized parameters, and we were able to make a variety of different nano array structures. So these are all about 100 nanometers in size. We can make these more complex structures. And this is just loading an image and using a lithography software in software that most AFMs have. And it's really just one pass. It's quite impressive, I think. So we decided to see if we could make a nanocapacitor array. So we deposited a thin layer of metal on top of it. We don't really have nanofab facilities in our university. And so we had a little bit of a delamination problem, as you might imagine. But we were able to make an array of nanocapacitors in a way. They're not isolated from each other. But then here's our PFM image, and we can show that we can switch them up and down into these checkerboard patterns. So everything switches, everything still remains ferroelectric. And so we were kind of happy with that result. And we hope to do more in the future in this area. So I hope that I've shown you that we think that with an application of force, you can affect switching voltage and current, that AFM-based machining can be used to fabricate a range of nanostructures, and that the ferroelectricity of these machined nano islands can be retained, and that I think for anyone trying to do this, just you can very quickly go through a range of different parameters to figure out what's the optimum for your target nanostructure or surface that you want to do. So you can control the depth, you can control the width by playing around with the velocity and the angle and the force that you're applying. And that will depend on the material that you're looking at. So just to thank the funding agencies. So this work was supported by Science Foundation Ireland and also the China Scholarship Council, and has collaborations across the world. So thanks for your attention.
All right, thank you so much, Brian, for your exciting talk. So we have two questions for you. The first one is coming from Satyam Latva. And Satyam is asking, how did you calculate the error margins and why are they so large for the 500 and 750 newtons values?
So I'm not sure, is this for the ferroelectric switching?
That's what I'm not sure. Satyam, if you are there, you can, yes, this is, Satyam is saying.
Okay. Yeah, so the errors are coming from doing multiple loops on different locations of the sample. So it's kind of like an average, and if there is more variability for that particular force, at higher forces, it's possible that the tip slips a little bit, so that could lead to some variability as well.
All right, thank you. And so let's take one more question. So there is a short question coming from Nikita Chetri, and Nikita is asking, does this procedure damage the tip?
So we do a tip reconstruction by looking at an array of sharp needle calibration sample, and we can see that the tip doesn't change very much over time. And I should also highlight that what we're doing is after we do the machining, there's actually pileup, and we remove the pileup with the same tip, and the tip shape tends to help the pileup move away from the apex of the probe. And the apex of the probe remains relatively as sharp as when we started.